Hello guys, if you're meeting me for the first time, I am the founder of the MAFA organization, an organization whose primary aim is to promote the study of mathematics in secondary schools and in universities. So in this video, we are going to be looking at the entrance examination into the National Advanced School of Engineering Yaounde, and we are going to be solving the mathematics paper 1 questions of the 2022 session. So without wasting much of your time, let's get started. This paper was divided into 2 exercises and a problem. Okay, so we are going to begin with the exercise. It was exercise number 1 and it was allocated for 4.5 points. Alright, here is exercise 1 and it reads, the complex plane is defined in an orthonormal system OUV given that A1, A2, A3, A4 is a convex quadrilateral where A1, A2, A3 and A4 are points with affixes A1, A2, A3 and A4 respectively. By applying the Gauss method, determine the complex numbers Z1, Z2, Z3 and Z4 of the following system. That is the system displayed to you. Roman 1. Show that there exists a convex quadrilateral M1, M2, M3, M4 where the midpoints of the sides are the points A1, A2, A3 and A4 if and only if the quadrilateral A1, A2, A3, A4 is a parallelogram. Roman 2. Show that A1, A2, A3 is an equilateral triangle if and only if A1 squared plus A2 squared plus A3 squared is equal to A1, A2 plus A1, A3 plus A2, A3. Alright, so the solutions are going to be coupled with the analysis of equations. So do well to comment in the comment section when you don't get an explanation. I am going to reply to you instantly. Alright, so we are going to begin with the first question, which is asking us to apply the Gauss method to determine the complex numbers Z1 till Z4 of the system, and this is the system that's been given to us. Alright, so first of all, the system that has been given to us can be converted into a metric system where we generate a 4x4 matrix since we have 4 unknowns, and we try to apply the method that has been specified to get the complex numbers Z1, Z2, Z3 and Z4. So I'm going to pick the coefficients Z1, Z2, Z3 and Z4, and then I'm going to write my system as a metric system. So first of all, let's begin with Z1. So I pick out the coefficients of Z1 in the first equation, of Z2 in the first equation, of Z3 and Z4 in the first equation, and I do same for all the equations. So Z1 in the first equation, the coefficient is 1. For Z2 it is 1. For Z3 and Z4 they are not present, so their coefficients are zeros. Now for the second equation, there is no Z1 present, there is no Z4 present, so we have the coefficients of Z1 and of Z2 and Z3 to be 1 and 1 respectively. Now in the third equation, there is no Z1 and Z2 present, so we have just the coefficients of Z3 and Z4. And in the last equation, there is no Z2 and Z3 present, so we have just the coefficients of Z1 and Z4. So this brings us back to our system. Alright, so first of all, I'm going to tell you guys that the matrix of this system has a determinant which is equal to 0, meaning that the matrix is a singular matrix, and whenever there is a singular matrix and there is inconsistency in the solutions, then we can clearly conclude that there is no solution to this system. So this is a 4x4 matrix, and you can actually do you can do some rough work to calculate the determinant of the matrix, and you're going to identify that the determinant of this matrix is 0, and since it is 0 and there is inconsistency of in the solutions, that's inconsistency of the equations, then we can clearly conclude that there is no Z1, Z2, Z3 and Z4 such that those 4 complex numbers satisfies these 4 equations at the same time. But nevertheless, I'm still going to explain the Gaussian elimination method, otherwise called the Gauss method, using another example. Alright, and with that said, we cannot actually solve Roman 1 of the equation, because to solve Roman 1 of the equation we actually need those complex numbers z1, z2, z3 and z4. But like I said, I am going to use the Gaussian elimination method in a different system to explain to you what the method is all about. Okay, so in the Gaussian elimination method, when we have our system written in this form, all we have to do is to make sure that all the elements below this leading diagonal line are all zeros, or above are all zeros, but it's always preferable to work with the elements below. That is, you transform the elements below this line to be 0. So we clearly see that the only element here which is not 0 is this element here. So we need to try by all costs to convert this element to 0. But nevertheless, on our way, if these other elements tend to different numbers, we are also going to apply some things that will convert them back to 0. So at the end of the day, our main objective is to convert all the elements below this leading diagonal line to be zeros. Alright, so I'm going to define the horizontal as rows, right? Horizontals are rows and verticals are columns. So the horizontal arrangements, I'm going to call the first one row 1, I'm going to call the second one row 2, I'm going to call the third one row 3, and I'm going to call the last one row 4. Now for me to actually convert these elements to 0, I'm going to begin with the element which is not 0 here, and I see what I can do to convert it to 0. So for the very first step, what I'm going to do is that I'm going to take row 1 minus row 4 to give me row 4. This application simply means that row 4 remains row 4 is a row which is going to be changing, but the rest of the rows are going to remain unchanged. Okay, I'm doing that because when I take the first element 1 here minus this one here, I'm going to get a 0, which will now convert the 1 to 0, which was my initial objective. So doing that, we are going to see that all the other rows, row 1 to row 3, will remain constant, but what is going to be changing is only row 4, because my application says that when I do the difference of row 1 and row 4, I'm going to get row 4. So you see the elements of row 1, row 2 and row 3 remain constant, but just the elements of row 4 are changing. Let us do the difference of those elements and see. Row 1 minus row 4 means I need to take 1 minus 1, which will give me 0. I need to take 1 minus 0, which will give me 1. I need to take 0 minus 0, which will give me 0, and I'm going to take 0 minus negative 1, which will give me 1. Now we clearly see that this is still our leading diagonal line, and this 1 here is a disturbing factor, so we need to convert it to a 0. And to convert it to a 0, if we use row 1 again, then this other element is going to change, so we are now going to use row 2. So for step 2, we are going to take row 2 minus row 4 to give us row 4. And remember that when you're doing this, you don't involve yourself again with the original matrix. No, you involve yourself with the new matrix you have gotten. So row 2 minus row 4 will give us row 4, because row 2 there is a 0 here which will cancel. In fact, it has no effect on this element, but this one here is going to cancel off with this one here, and then we see what we have at the end of the day. So doing that, we said that row 2 minus row 4 is going to give us row 4, and with that it means that row 1, row 2 and row 3 will remain constant while row 4 changes. So if we do the difference, you are going to have for row 2, 0 minus 0 gives us 0, 1 minus 1 gives us 0, 1 minus 0 gives us 1, and 0 minus 1 gives us negative 1. At the end of the day, we still have another disturbing factor, because this line here is still our leading diagonal. So we now have to make this disturbing factor here to become 0. So for step 3, we are now going to use row 3 minus row 4 to give us row 4, meaning that the rest of the rows are going to remain constant, but row 4 is going to change. Alright, so if you do the difference, you are going to have a change only in row 4. So row 1, row 2 and row 3 remain constant. Now my application says I need to subtract row 4 from row 3, and the result should give me row 4. So I need to take 0 minus 0 to give me 0. 0 minus 0 to give me 0, 1 minus 1 to give me 0, and 1 minus negative 1 to give me 2. So I have completed the objective of the question actually. All right, so you see that the line, the leading diagonal line, if you draw a line, you're going to identify that all the elements below this leading diagonal line are all zeros. So it helps me to solve the system. But nevertheless, there is actually what we call the augmented matrix, which because of some difficulties I faced in presenting these solutions, I could not actually bring out that matrix. So doing all of this, okay, we are also supposed to be doing it to the right hand side of the equation. So I'm going to do the right hand side in another explanation, and then we combine the system together. All right, so the right hand side is what we have: 2a1, 2a2, 2a3, and 2a4. So I'm still going to call them row 1, row 2, row 3, and row 4. Now my first step was that I was taking row 1 minus row 4 to give me row 4. So I performed that application in the right hand side. I do the same thing for step 2, where I did row 2 minus row 4 to give me row 4. I perform the same calculation and then I get this. I do the same thing for step 3, where I took row 3 minus row 4 to give me row 4, and I had this final matrix. All right, so this is the matrix that we have on our right hand side, and the matrix we had on our left hand side, that's the matrix of the system, was given already. We had it already, but nevertheless I'm still going to present it. All right, so this is our new matrix that will be on the left hand side, and this is the new matrix that will be on the right hand side. So my system can be converted to the matrix on the left hand side multiplied by the matrix of the solutions to be equal to the matrix on the right hand side. So if we multiply, we have back a system which will enable us to easily solve for Z4, then Z3, then Z2, then Z1. All right, so at the end of the day, if we multiply back this, we are going to have Z1 plus Z2 equal to 2A1, Z3 plus Z4 equal to 2A2, Z2 plus Z3 equal to 2A2, Z3 plus Z4 equal to 2A3, and 2Z4 equal to all of this. So you see, the purpose was that we should easily get Z4. So after getting Z4, we can divide all through by 2. We get Z4 to be this quantity. We now replace Z4 in the third equation and we solve for Z3. We get Z3 to be this. We now replace Z3 in the second equation and we solve for Z2. And we finally replace Z2 in the first equation and we solve for Z1. So with respect to this system that I proposed, we have that the solutions are Z4 equal to this, Z3 equal to this, Z2 equal to this, and Z1 equal to this. But with the question that was given in the concours itself, it was not possible. But you just see, I just changed and I had a minus sign here. So that is it for the quotient elimination method. Alright, so like I said, the Roman 1 part of the equation can't be solved because we actually need the correct system of the first part of the equation to be able to get Z1, Z2, Z3, and Z4, and then we do the application in Roman 2. So we are going to dive straight away into looking at the solution to Roman 3, which says that we should show that A1, A2, A3 is an equilateral triangle if and only if the sum of the squares of the affixes is equal to the product of the affixes. So A1, A2 plus A2, A1, A3 plus A2, A3. That's the sum of the product of the affixes. Alright, so this proof is actually very important and it is very well designed for you to understand better. So it is actually telling us to relate the affixes of an equilateral triangle. A1, A2, A3 is an equilateral triangle, and we already told that small a1, small a2, small a3 are the affixes of the points A1, A2, and A3. So we need to find a way that will enable us to relate these affixes, because A1 is the affix of capital A1, A2 is the affix of capital A2, and A3 is the affix of capital A3. So what then do we do? So first of all, the first step is that I'm going to choose an arbitrary equilateral triangle, and then I just label. And you should remember that the points on any triangle are always labeled in the anti-clockwise direction, meaning that all triangles are directly oriented. Directly oriented means if I begin A1 from here, I'm going to indicate, like I'm going to put the other points in the anti-clockwise direction. So this is A1, so I need to go in this direction, A2 and A3. If you do A1, A2 and A3, is not really appropriate, because it is kind of a definition that triangles are directly oriented in most cases. Now, since this is an equilateral triangle, it means that all the sides have equal lengths, and the angle between the line A1, A2 and A1, A3 is simply 60 degrees. The angle between the line A1, A3 and A3, A2 is also 60 degrees, and the angle between the line A1, A2 and A2, A3 is 60 degrees, because it is an equilateral triangle. Equal sides and equal angles between the sides. Alright, so since I need to relate the affixes of these points, the only thing that will help me to relate the affixes of these points are complex transformations. So this is an equilateral triangle, just an arbitrary one, to explain to you the concept that is going to be applied here. So we have to recall that if I want to write the equation of a rotation that is centered at the point omega, then the equation of that rotation, which is relating the point and its image, is simply z prime minus z omega equal to e to the I alpha into z minus z omega. Alpha is the angle of rotation, z is a point that is transformed to z prime, and z omega is the affix of the center of the transformation. So you should note that involving with rotations, the scale factor is always equal to 1. So there is no enlargement, there is no reduction, there is just a rotation. So the angle of rotation is there, as well as the center of the rotation. So those are the main two characteristics of every rotation. So now we have to actually relate the points, the affixes of these points, and for us to do that, we clearly see that we can transform any points to any point, because the side lengths of all these sides are all the same. So there is no scale factor. That's, in fact, the scale factor is equal to 1. That's what I'm trying to say. Meaning that if a point is transformed to another in this figure, then there is no increase or decrease in length. The distance between the point and the center will be the same as the distance between the center and the image. So that defines clearly a rotation. Alright, in fact, it's an isometry, okay, because they conserve distances. Alright, so step 2 is that we are going to define rotations. So I'm going to define a rotation whose center is at A3 and another rotation whose center is at A1. You could also define your own rotation whose center is at A2, but I'm just choosing what I choose already. Alright, so my first rotation is centered at A3, is transforming the point A1 right to A2. So we clearly see that the angle of rotation, since I'm transforming A1 to A2, the angle of rotation is the exterior angle between the lines A1, A3 and A3, A2, which that angle that angle is simply 360 minus 60, which is 300 degrees. But since I am rotating in the clockwise direction, that angle is considered to be negative, so it's going to be negative 300 degrees. But negative 300 degrees simply corresponds to positive 60 degrees. So it means I can use pi on 3, or use negative 300 degrees. In fact, convert it to pi, you're going to have the same response at the end of the day. Alright, so that rotation is taking the point A1 to A2 through the angle of pi on 3, and the center of the rotation is the point A3. So from the definition of my rotation, I'm going to have that when I input the complex number, in fact, if I want to find the image of the point A2 is simply the image of the point A1 is a point A2, and the center of my rotation is A3. So from the definition of the rotation we have had above, we need to do what? The difference between the image, the affix of the image, and the affix of the center. The affix of the image is small a2 because it's the affix of the point A2, and the affix of the center is small a3 because it is the affix of the point capital of the point A3. Now my angle of rotation is pi ln 3, and then we have the affix of the point, which is A1, minus the affix of the center. So I can call that equation 1. Now my next rotation is going to be taking the point A1 to, I'm going to be taking the point A2 to the point A3, passing through the center A1. So I'm going to be taking A2 to A3, passing through A1. What is our angle of rotation? Is the exterior angle between these lines. That is the line joining the center and the points with the line. The angle of rotation is the exterior angle of the line joining the center and the points, and the line joining the center and the image. So it is this exterior angle outside here, okay, but that exterior angle is still going to be 300, and since I am still rotating in the clockwise direction, the angle is negative and is going to be negative 300, and the negative 300 corresponds to positive 60. You see, this is now another direction, so either I use negative 300 or positive 60, you are still correct. Just note that whenever you're rotating in the clockwise direction, the angles are negative, and in the anti-clockwise direction, the angles are positive. Alright, so my arrow 2 is a rotation that is centered at the point A2, taking the point A3, is centered at the point A1, taking the point A2 to the point A3 through the angle 60 degrees as pi ln 3. So from the definition we have that the image of the point A2 is A3, and from our definition we have that the difference between the affix of the image, which is A3, and the affix of the center is equal to e to the power I times the angle of rotation times the difference between the affix of the point that is being transformed and the affix of the center. So we can call this equation 2. Now the next step is that we have to eliminate e to the power I pi ln 3 from these equations, and eliminating it will help us to relate the affixes of these points, meaning we are going to relate A2, A3, A1, okay, because that's the e to the I pi ln 3 is a disturbing factor which is common in both equations. So if you can eliminate it, then we are just going to be left with an equation that has A1, A2, and A3, and then we work towards obtaining our proof. Alright, so we have these two equations, and the first equation is possible if and only if we can divide both sides by A1 minus A3, and we get this. The second equation is possible if and only if we can divide both sides by A2 minus A1, and we get this. So if e to the I pi ln 3 is this and e to the I pi ln 3 is this, it therefore means that the two equations are the same. So we can cross multiply, and then if we expand correctly and break like terms together, we are going to arrive at A1 squared plus A2 squared plus A3 squared equal to A1 A2 plus A1 A3 plus A2 A3, which is actually what we have to prove. So we have proven that A1 A2 A3 is an equilateral triangle if and only if the sum of the squares of the affixes is equal to the sum of the product of the affixes of those points. Alright, now some of you might be thinking that why did I just introduce the biconditional statement that is a double implication. Now this is the thing. So actually some of you might be trying to prove that since it is a double implication, you might be trying to say that okay, we are going to prove that if one happens then the other one happens, then we are going to prove now the reverse. But actually if you want to prove it that way, you can go ahead and prove it that way. But you see, I already introduced my my double implications already, because for this to be an equilateral, in fact this is an equilateral triangle if and only if these rotations are defined. So it means that the implication sign is already there, so I need not to prove both conditions again because it's going to take a lot of time to do that. Okay, so for this to be an equilateral triangle, this is an equilateral triangle if and only if these two rotations are defined, and when we work out with that, we arrive at a proof at the end of the day. Okay, so that was all about exercise 1. It was allocated for 4.5 points, and we saw that the first question had a problem with the system, and I used a different system to analyze and give you the key concept on the Gaussian elimination. So now we are beginning exercise 2, which is 5.5 points. Alright, exercise 2 reads: 1. Consider the complex plane with orthonormal reference OUV where 1 centimeter equal to 1 unit on both axes. For x being the set of real numbers, we are to express this polynomial as a product of two polynomials of degree 2 with real coefficients. Let p of z be equal to this polynomial for z belonging to C. A. Show that if z0 is a complex root of p of z equal to 0, then a conjugate z0 bar is also a root. Justify also that the product of z minus z0 and z minus z0 bar is a polynomial with real coefficients. B. Show that p of z is equal to z squared plus z plus 2 all squared plus 1 minus z all squared. C. Solve in C the equation z squared plus z plus 2 plus I into 1 minus z equal to 0. D. Deduce all the complex roots of p of z equal to 0. Explain. E. Express this polynomial as a product of the two polynomials as required. Question 2. Consider in a complex plane the points A to D with respective affixes -1 plus 2i to -1 minus 2i. A. Is there a circle that passes through the points A to D? If yes, describe it completely. B. The quadrilateral ABCD represents a piece of land whose scale is 1:10,000. Calculate in meters squared the area of the piece of land. Alright, so we are going to have a brief analysis of the question alongside the solution. Okay, so we are going to begin with this first question, so we dive straight away to the solution. Okay, so it reads, I'm going to read it again. The objective, in fact, let me just give you guys the objective as it is written in the equation. The objective is to express x to the power 4 plus 2x cubed plus 6x squared plus 2x plus 5 as a product of two polynomials of degree 2 with real coefficients. And then you have been given various steps that will guide you to do that. So the first question is asking us to show that if z0 is a complex root of p of z equal to 0, then the conjugate is also a root. Justify also that the product of z minus z0 and z minus z0 bar is a polynomial with real coefficients. So let us begin with the first part, that is showing that z0 is a root of p of z, z0 bar is a root of p of z equal to 0, provided z0 is also a root. Alright, so what do we mean by saying that z0 is a root, is a complex root of the polynomial of the equation p of z equal to 0? It simply means that p of z0 is equal to 0. Now p of z0 equal to z0, p of z0 equal to 0 means that I just need to come to my p of z and I replace z with z0. I add up the terms and I equate it to 0. Now the objective is to prove that the conjugate of that complex number is also a root. So what we are going to do is that we are going to take conjugate on both sides of the equation. So we take conjugate on the left hand side and we take conjugate on the right hand side. But I would like us to recall that the sum of the conjugates of complex numbers is the conjugate of a sum is a sum of the conjugates. So it therefore means that I'm going to distribute the conjugate to all the complex numbers, and the conjugate of a real number is still the real number because he has no imaginary part. Remember that the conjugate of a complex number is gotten just by changing the sign of the imaginary part. But since 0 is purely real, then clearly it has the conjugate of any purely real number is that number. Alright, so at the end of the day, we have z0 bar all to the power 4 plus 2z0 bar all cubed plus 6z0 bar all squared plus 5z0 bar equal to 0. And we can deduce from here that p of z0 bar is equal to 0. Hence, z0 bar is also a root to the equation p of z equal to 0. So we have proven. Now, the second part of the equation is asking us to justify also that the product of z minus z0 and z minus z0 bar is a polynomial with real coefficients. So we are going to let that product to be f of z, and then now if we multiply, we just have z times z, it gives us z squared. We factorize the z from the next multiple and we get negative z into z0 plus z0 bar, then plus the product of z0 and z0 bar. Now our next recall is that if I add two complex numbers, meaning if I add a complex number to its conjugate, I get a purely real complex number. Okay, so x plus iy plus x minus iy simply gives me 2x. X plus iy, x minus iy is a conjugate of x plus iy. Alright, also if I multiply a complex number with its conjugate, I simply get a purely real number, meaning if you multiply you get x squared plus y squared. Remember that x and y are all real numbers, so 2x will be real and x squared plus y squared will also be real. Now what are the coefficients in this polynomial? We have 1, which is a coefficient of z squared, which is a real number. We have the coefficient of negative z, which is z0 plus z0 bar, which is purely real because you have seen that whenever we add a complex number to its conjugate, we get a purely real complex number. And finally, what is z0 times z0 bar? It is also purely real because of this condition. So with that, we clearly see that our f of z is a polynomial with real coefficients. Polynomial because all the parts of z are all positive, and it is actually a quadratic complex polynomial, and all the coefficients of the variable are all real. So we have proven that. Okay, now the next part of the equation, which is b, is asking us to show that p of z is equal to z squared plus z plus 2 all squared plus 1 minus z all that squared. Alright, so z squared plus z plus 2 all squared plus 1 minus z all squared can be simplified by simply multiplying z squared plus z plus 2 with itself and 1 minus z with itself. If you multiply that, you're going to simply get this equation. If you bring the like terms together, you're going to get this expression on the left hand side, which is equivalent to p of z. So we can boldly say that our p of z is z squared plus z plus 2 all squared plus 1 minus z all squared. Now the c part of the equation is asking us to solve in a set of complex numbers the equation z squared plus z plus 2 plus I into 1 minus z equal to 0. So the first thing to do is that we are going to bring the terms in z together, because this is a quadratic complex equation where we need to solve for z, and it is preferable to use the formula method. So this equation means that we just need to bring the coefficients of z together and we factorize, and then we have to write it in as a quadratic equation. Alright, so from there now we can look for the discriminant, which is b squared 1 minus I all squared minus 4ac. Our a is 1 and our c is 2 plus I. If we multiply and simplify, we get our discriminant to be negative 6i minus 8. But the quadratic formula says that our z is equal to negative b, which is negative of 1 minus I, that gives us I minus 1, plus or minus the square root of the discriminant divided by 2a. So all we are left to do is to find the square root of the discriminant, which is the square root of negative 6i minus 8. Alright, So how then do we find the square root of a complex number? So let us let a plus bi be equal to that square root where a and b are all real numbers. If we square both sides of the equation and bring the real parts together and the imaginary parts together, we equate the real part to the real part and the imaginary part to the imaginary part. We try to divide and we look for a in the second equation. Then we now replace that value of a in the first equation, and then we simplify the equation. We are going to get b to be plus or minus 3. But how do we simplify this equation? Simplifying this equation, we just need to obtain an equation like this, where we multiply all through by b squared, and then we bring everything to one side of the equation and we solve for b squared. Solving for b squared will give you 9. Okay, so if you factorize, you get b squared minus 9 times b squared plus 1 equal to 0. Since b squared plus 1 cannot be 0 because you cannot add two positive numbers and you get 0, therefore it means this product is possible when b squared minus 9 is 0. So b gives us plus or minus 3. Plus or minus 3 is a real number, so the two values of b are accepted. From there, we can now get the values of a. So we need to replace our b with plus or minus 3. Our a becomes minus plus 1, because if you replace b with plus 3, your a is minus 1. That's why the minus comes first and the b has plus 3. And if you replace your b with negative 3, your a becomes plus 1. That's why the minus 3 is second and the plus 1 is also second. So from there, we can have that the square root of our complex number will either be negative 1 plus 3i, because it is a plus bi. When a is negative 1, our b is positive 3. Or we have that when a is 1, our b is negative 3. So we can use any of them, but I decided to use negative 1 plus 3i. So using that, we have that our z will be negative, will be I minus 1, all divided by 2, plus or minus the negative 1 plus 3i divided by 2. You add the real part, you add the imaginary part, and you consider the plus or minus. You are going to get that z is equal to negative 1 plus 2i and negative I. So these are the two solutions to the equation z squared plus z plus 2 plus I into 1 minus z equal to 0. Alright, the last but not the least question of exercise 2, it says that we should deduce all the complex roots of p of z equal to 0, and we should explain our deduction. Alright, so p of z equal to, our p of z was already proven to be z squared plus z plus 2 all squared plus 1 minus z all squared. But I'm going to like us to do some little recalls. Now, if we have the product of a complex number and its conjugate, we are simply going to get the sum of the squares of the real part and the imaginary part. If you look at this relationship, you clearly see that here you are summing two polynomials. Okay, you're summing the squares of two polynomials. All right, so if I do a little substitution, like if I take my a to be z squared plus z plus 2 and I take my b to be 1 minus z, it therefore means that my p of z is simply a squared plus b squared, because a squared is this quantity squared, which is this quantity here, and b squared is this quantity here, provided a and b are the interiors. All right, so from there, what can we deduce? We can deduce that our p of z can be written as the product of a plus bi and a minus bi. All right, so our a is z squared plus z plus 2. You have your I there, and your b is 1 minus z. You have clearly seen that when you multiply the two polynomials, you're going to get the sum of the squares of the real part and the imaginary part. So the real part here is z squared plus z plus 2, and the imaginary part is 1 minus z. So it therefore means that this property will always hold. If you multiply these two polynomials, you're going to get back the polynomial p of z. Now, this first quantity here, like we said, it is a. The second quantity is ib. The next quantity is a, and the next quantity is ib. So we clearly see that you have something like a plus bi times a minus bi. You will definitely get a squared plus b squared, where your a is z squared plus z plus 2 and your b is 1 minus z. Alright, so from there, solving the equation p of z equal to 0, it means that we have to equate both polynomials, complex polynomials, to 0. So we can call the first one equation A and call the second one equation B. But I will like us to look keenly at these two equations. We see that if we take the conjugate of the first equation, we are going to get the second equation. This is the explanation. This is my equation A, okay. Now if I take the conjugate on all that, if I take the conjugate of this equation, I'm just going to use my property of the distribution of the conjugates, and I'm going to get conjugate of z squared plus conjugate of z. Conjugate of 2 is 2. Now when I take the conjugate of I, okay, that's because this is my imaginary part. So taking the conjugate, I just need to change the sign of the imaginary part. So I just have negative I into 1 minus the conjugate of z equal to 0. So we clearly now see that if z is a solution of equation A, then the conjugate will be a solution of equation B, because equation B is simply the conjugate of equation A. If you look at it keenly, look at here, z squared bar in equation A, it is z. Okay, it is the same z that we are talking about, but equation B has its conjugate distributed. Alright, so it means that z being a solution of equation A, then automatically the conjugate is a solution of equation B, because if you see here, the solution of this equation is simply z bar, because that's what is in function here, z bar, okay, and this is clearly equation B, and the z here is actually the same as the z of equation A. So to get the solutions of equation B, we just need to conjugate the solutions of equation A. Now we should also recall that we already solved this system previously, and we had our z to be negative 1 plus 2i and negative I. So solving, that is for equation A. So solving equation B simply means that we just need to conjugate the solutions of equation A, and we get the conjugate of negative 1 plus 2i, which is negative 1 minus 2i, and the conjugate of negative I, which is positive I, that is for B. It therefore means that all the roots to P of Z equal to 0 are negative 1 plus 2i, negative I, negative 1 minus 2i, and positive I. So those are the 4 complex roots that we have. Okay, the last part of the equation is asking us to express x to the power 4 plus 2x cubed plus 6x squared plus 2x plus 5 as a product of two polynomials as required. In fact, that was the objective of the equation. Alright, so our P of Z is equal to this polynomial where Z is a real number, and we should recall that if the roots, in fact the roots of our P of Z are simply this and this. Now, since these are roots, it means that the factors, if negative 1 plus 2i is a root, it means Z minus into negative 1 plus 2i is a factor. So it therefore means that Z minus all of this means Z plus 1 then minus 2i is a factor. Now, if negative 1 minus 2i is a root, it means Z minus it is a factor. So it means if we take Z minus all of this, okay, that's, sorry, here is supposed to be a plus sign. So Z minus negative 1 then minus negative 2i. So we are going to get Z plus 1 plus 2i to also be a root, to also be a factor, sorry. Similarly, if Z equal to negative I is a root, it means Z minus negative I is a factor, that's Z plus I. And if Z equal to I is a root, it means Z minus I is a factor. So these are the 4 factors, and we know that every polynomial can be written as a product of its factors. Remember, the sign here is positive. So every polynomial can be written as a product of its factors, meaning that I can call this one the product of, in fact, you see that here I am actually multiplying Z minus Z0 with Z minus Z0 bar, because these are conjugates, okay, which you can clearly see the relationship between the first question we solved. So here is Z0, and here, which is positive 1, let me do the correction there. There's supposed to be positive 1 is the conjugate. So here's positive, here is positive. as well. All right, so from there we clearly see that we are doing the product of a complex number and the conjugate. That's the product of the difference between z minus z0 and z minus z0 bar. The same thing here, we call our z1 to be I or negative I, and we are doing the product of z minus the complex number with z minus the conjugate of the complex number. So if we multiply and then we use that our property that we proved in the first equation, we have that this is going to give us z squared minus z into the sum of the complex number and the conjugate plus the product of both of them. We apply the same thing here. So we can easily express this as z squared minus z into, if we sum the complex number and the conjugate, so we sum -1 plus -1 will give us -2. 2i minus 2i is 0, so it's -2. But now the formula has a negative, so it becomes +2. If we multiply both of them, we already saw that we just need to sum the squares of the real part and the imaginary part. So we have 1 squared plus 2 squared to give us 5. The same thing here, if we add -i to i, we get 0, so there will not be there's not going to be any term in z. If you multiply -i and I, we get -i squared, which is +1. So it therefore means that our x to the power 4 plus 2x cubed plus 6x squared plus 2x plus 5 will be written as x squared plus 2x plus 5 times x squared plus 1, because you clearly see that p of z is the complex polynomial of this polynomial in the real variable. Okay, question 2. Consider in a complex plane the points a, b, c, and d with respective affixes -1 plus 2i, I, -i, and -1 minus 2i. Question A. Is there a circle that passes through the points a, b, c, and d? If yes, describe it completely. So first, I will need to enlighten you guys on this concept. Now, they are just trying to tell you to verify if the points A, B, C, and D are on the same circle, meaning that you're trying to verify if these points are co-cyclic. So points that fall on the same circle are said to be co-cyclic. Points that fall on the same line are said to be aligned or collinear. Points that fall on a plane are said to be coplanar. Alright, so for these 4 points to be co-cyclic, note this condition very well. The argument of ZB of the complex number of the ratio between the complex number ZBC and ZAC minus the argument of the ratio between the complex number ZBD and ZAD must be 0 in mod 2 pi's, meaning that it could be 0, it could be 2 pi, it could be 4 pi, and so on and so forth. So this clearly means that the complex number is purely real. Which complex number? The complex number ZB, in fact, the complex number this interior divided by this interior. If I take this divided by this denominator goes to the numerator, and we have it here, and the numerator goes to the denominator. And if the argument of this complex number here is equal to 0, it therefore means that that complex number is purely real. Alright, so let us verify. ZB minus ZC over ZA minus ZC, we just need to take the difference between the affixes. So ZB was I minus ZC is negative I divided by ZA, -1 plus 2i minus ZC, negative I. If we simplify, we get this. We can call this Z1. Now we do the ratio between ZBD minus ZD, ZB minus ZD, and ZA minus ZD. Our ZB is I and our ZD is -1 minus 2i. Our ZA is -1 plus 2i and our ZD is -1 minus 2i. If we simplify, we get this and we call it Z2. Now we have to recall that the argument of Z1 minus the argument of Z2 is the argument of Z1 divided by Z2. It therefore means that the argument that we are looking for here is simply the argument of Z1 divided by Z2. And to change the division sign to multiplication, we need to invert the complex number Z2. So we need to take 4i to the numerator and 1 plus 3i to the denominator. If we multiply the numerators and multiply the denominators, we are going to get and rationalize. We are going to get that this argument is the argument of 8 divided by 10, and clearly 8 divided by 10 is purely real, so that argument must give us 0. And with that said, we can conclude that the points A, B, C, and D are cocyclic, that is, they belong to the same circle. Now, how then do we describe this circle completely? It means we should give the equation of the circle stating its radius and its center. So let us define generally the equation of the circle that contains these 4 points. Let us say the circle is centered at the point x0, y0, and the radius of the circle is r. Now we have that the point A belongs to that circle provided the x and the y coordinate of the point A actually satisfies the equation of the circle. The point A has affix -1 plus 2i, so the point itself is the point -1, 2. So we need to replace x with -1 and we replace y with 2. We get the first equation factorial 1. Now we also have that the point B belongs to the circle. The point B has affix I, so the point is 0, 1. So we need to replace x with 0 and we replace y with 1. We get equation double factorial. And then we now also see that the point C also belongs to the circle, and then the point C has affix -I, so the point itself is the point 0, -1. So we need to replace x with 0, we replace y with -1, we get our triple factorial equation. Now we have to solve these 3 equations simultaneously, and then at the end of the day we get the equation of the circle, and we further verify if the point D belongs to that equation to clearly that is to clearly justify that yes, all these points pass through that circle. In fact, the circle passes through these points. All right, so if we take the difference between equation 2 and equation 3, we are going to get something like this, where if we solve for y0, our y0 is going to give us 0. Now if we replace y0 in equation 1 and equation 2, we are going to get this system of equations where when we solve, we are going to get that our x0 will be -2 and our r is going to be the square root of 5. So it means that circle is x plus 2 all squared plus y squared equal to 5. Now you can further verify if the point D belongs to the circle, meaning replace x with -1 and replace y with -2 and see if the left hand side simplifies to give you the right hand side. So this circle described completely is a circle centered at a point -2, 0, whose radius is 5. Okay, the last part of the equation is asking us to calculate the area of the piece of land ABCD, which is in the form of a quadrilateral, and the land is on a scale. The piece of land is actually on a surface whose scale is 1:10,000. Alright, so we should recall that the equation of our circle is given by this, and we have our points. So I already plotted the circle and the points together, and I came up with a quadrilateral. So I'm just going to display the figure to you. So if you plot the point A, -1, 2, you get it here. The point B, 0, 1. The point C, -1, 0. And the point Z, -1, -2. If you link the points together, you're going to construct a circle passing through the points. Now the objective is to calculate the area of ABCD, and we clearly see that ABCD is a trapezium, and the area of that trapezium is half times the sum of the parallel sides times the height. The parallel sides are AD and BC, and the height is O, that's the distance, this distance here. We are going to define it later. We can just call it H. Now we need to first of all find AD, BC, and H, and then we just impute into the formula. Alright, so the distance AD is simply the modulus of the complex number ZAD. Alright, so what's the modulus of ZAD? It is the modulus of ZD minus ZA, which is the modulus of our ZD is -1 minus 2i minus -1 will give us -2. minus negative 1 plus 2i is going to give us negative 4i, and the modulus is 4. So it means the distance AD is 4 units. What about the distance BC? Is the modulus of the complex number ZBC, which is the modulus of ZC minus ZB. If you do the ratio and you find the modulus, you get 2 units. Now we can now call this point E, and the coordinates of E will be negative 1, 0, because E has the same x coordinate as A and Z, and since it is on the x-axis, it means its y coordinate is 0. So we see that the height of that trapezium is simply OE. So H is equal to OE, and it is clear from here that it is 1 centimeter, the distance. Alright, so from there now, what's going to be the area of our trapezium? It's going to be half times the sum of the parallel sides, 4 plus 2, times the height, now in square units. So if you simplify, we get that the area is 3 square units. But now there is a problem. This area is supposed to be in meter squared, so we need to take into consideration the scale of the piece of land. Alright, so let us interpret our scale. Our scale says that we are working with 1:10,000. What does this mean? It means that 1 unit represents 10,000 centimeters. Now 10,000 centimeters to meters, you divide by 100, it means that 1 unit represents 100 centimeters. 100 meters, converting centimeters to meters. So 1 unit is 10,000 centimeters, which is in turn equal to 100 meters. Now, since we need 3 square units, it means we first of all need to find 1 square unit. So we can square both sides, and we have that 1 square unit represents 10 to the power 4 meters squared. Therefore, 3 square units will be 3 times 10 to the power 4 meters squared. So at the end of the day, we can conclude that the area of this piece of land is 30,000 meters squared. Alright, now we move on to the problem, which is 10 marks, and it is actually divided into 2 independent parts. Now this problem is divided into 2 independent parts, and it is allocated for 10 marks. So we are going to have a brief analysis of the problem and the solution alongside. Okay, so the problem, we begin with part A, which is 5 marks, and we are just going to see the equation together. Alright, so this is part A of the problem. It reads, ABC is a triangle in a complex plane with orthonormal coordinate system OUV. 1. Given that x, y, and z are complex numbers, all different such that they have the same modulus. Suppose that A, B, and C have affixes x, y, and z respectively. Question 1. Consider the point D with affix x plus y plus z. A. Show that y bar z minus y z bar and y plus z times y bar minus z bar are purely imaginary complex numbers, z. B. Show that AD, the vector AD, or the line A, the vector AD, and the vector BC are orthogonal, meaning perpendicular. Question 2. Show that D is the orthocenter of the triangle ABC. Capital 2. Suppose that A and B have affixes T plus IA and T plus IB, where A and B are real numbers with T different from 0 and B. Let A prime be the image of A after a rotation through pylon 2 about the origin O. Let B prime be the image of B after the rotation through negative pylon 2 about the origin O. Question 1. Determine in terms of T, A, and B the affixes of A prime and B prime. Question 2. Show that the median from the point O of the triangle OAB is the height of the triangle OA prime B prime. Okay, so we dive straight away to analyze the question and provide the solution. So we begin with the first part, which is asking us to show that y bar z minus yz bar and y plus z into y bar minus z bar are purely imaginary complex numbers. So the first thing we have to note is the definition of a purely imaginary complex number. So we say that the complex number z1 is purely imaginary if and only if z1 is negative of its conjugate. That is, summing the complex number with its conjugate, we always get 0. Alright, so let's begin with our complex number here, which is y bar z minus yz bar. So let's find the conjugate, and we use our property of conjugates, right? We need to distribute the conjugate, and then now from here we see that distributing a conjugate into the product, the conjugate is also distributed over the product. So we are going to have the conjugate of y, which is y, times the conjugate of z. Here we are going to have the conjugate of y times the conjugate of z, which is z. Now if we factorize a negative sign, we are going to have this to be y bar z minus y z bar, and we clearly see that y bar z minus y z bar will be negative into its conjugate, because this is our original complex number and this is the conjugate. So the conjugate is negative of the complex number, meaning that the complex number is also negative of the conjugate. So from this set, we have proven that the complex number this is purely imaginary. This is the representation of a purely imaginary complex number. Alright, now we have to also prove that the product of y plus z and y bar minus z bar is also purely imaginary. So if we do the product, we are going to have y bar minus yz bar plus zy bar minus zz bar. Now we should recall some certain things first, that the product of a complex number and its conjugate is simply the square of the modulus of that complex number. It can be proven. You can just take a complex number to be x plus iy, and you perform this and you're going to see the relationship. Alright, so it therefore means that y bar becomes the modulus of y squared and zz bar becomes the modulus of z squared. Now I can write this as y bar z minus yz bar, like this. Okay, now we should also recall that these complex numbers y and z have equal modulus. It therefore means that their squares are also equal in modulus. So it therefore means y bar, the modulus of y bar squared minus the modulus of the modulus of y squared minus the modulus of z squared is equal to 0, because they have the same modulus. So it therefore means that this product is simply equal to y bar z minus yz bar. But we have already proven that y bar z minus yz bar is a purely imaginary complex number. It therefore means in conclusion that this product is also going to be a purely imaginary complex number. So we can conclude that those two complex numbers are purely imaginary. Alright, next question. Show that the vectors AD and BC are orthogonal. Alright, so to first of all show that two vectors are orthogonal or two lines are orthogonal, we just need to show that the angle between them is 90, and in complex numbers, the definition of the angle between two lines is defined in terms of the argument. So the angle between two lines is simply the argument of the ratio between the affixes that make up those lines. Alright, so the angle between AD and BC is simply the argument of ZAD divided by ZBC. And for the two to be orthogonal, this argument should either give us plus pi on 2 in mode 2 pi or minus pi on 2 in mode 2 pi. We are taking mode 2 pi because you could get maybe 7 pi on 2. 7 pi on 2 is not in the range of the argument, okay, because argument lies between negative pi on pi. So we have to subtract 2 pi's from it till we arrive at a range between negative pi and pi. So that's why we are taking mode 2 pi. Alright, so we in fact, if you take the argument of a complex number and the result is plus or minus pi on 2, it therefore means that that complex number is a purely imaginary complex number. That's a definition. Alright, so let us find ZAD over ZBC. It is the difference between the affixes of A and Z divided by the difference between the affixes of B and C. Now, our D has affix x plus y plus z, and our A has affix x. So if we take x plus y plus z minus x, we are just going to get y plus z. the denominator, our b has affix y and our c has affix z. So our denominator, whether though I took, but it's supposed to be zc minus zb. Okay, so here is zc minus zb, and zc is z and zb is y. Now we factorize the negative sign and then we multiply the complex number, that's the top and bottom, by the conjugate of the denominator. We are just going to get the negative sign outside here. Now this complex number becomes y plus z on y minus z. We now multiply it with the conjugate of that denominator. In fact, we multiply it with the conjugate, which is y minus z all bar divided by y minus z all bar. Now we can distribute, or we can even simplify what it means by y minus z all bar. We distribute the conjugates to the separate complex numbers. We saw that property already. So the numerator becomes y bar minus z bar, and same goes to the denominator. Now from there we can now multiply the numerators and we multiply the denominators, and then we try to analyze together. Alright, some recalls again. Now we should recall that the complex number y bar z minus yz bar was already proven to be purely imaginary. This means that it can be written in the form bi, where b is a real number different from 0. It means there is no real part, so it is purely imaginary. So there is no real part as a plus bi, it is just bi. Alright, so you should also recall that we also proved that this complex number was also purely imaginary, meaning that it can be written in the form ai, alright, where a is a real number different from 0. There is no real part, you just have an imaginary part. The real part is 0. Alright, so from there, if you come back here, you clearly see that the numerator of this complex number, the numerator of our complex number here, is a purely imaginary complex number, and the denominator is purely real. Why is it purely real? Because we are multiplying a complex number and its conjugate. Whenever you multiply a complex number and its conjugate, you get a purely real complex number. So that is a definition. So it therefore means that we have purely imaginary divided by purely real. You're still going to get a purely imaginary complex number, because at the end of the day there will be no real part. You just still have an imaginary part. Alright, take for example, you take a purely imaginary bi divided by a. You have what? B divided by a times I. B on a is still a constant, we can call it c. So you see that we still have a purely imaginary complex number. It therefore means that this guy here is purely imaginary, and since it is purely imaginary, then its argument will give you plus or minus pi on 2, and we can conclude that those two lines are orthogonal. Okay, now the next part of the equation is asking us to show that D, which has affix x plus y plus z, is the orthocenter of the triangle ABC. Alright, so I'm going to pick out an arbitrary reference triangle just to explain, to tell you that if a point is the orthocenter of a triangle, it therefore means that the line AD must be perpendicular to BC. That is, AD is a perpendicular bisector of BC, because this AD is passing through the center, so it must divide the segment BC into two equal parts. So it's actually dividing at the midpoint, and it should be perpendicular to it. Same thing goes for the BD being perpendicular to AC, and same thing goes for CD being perpendicular to AB. Now, so we clearly see that if D is the orthocenter of this triangle ABC, then three things happen. First, AD and BC, that is AD and BC, are supposed to be orthogonal. Secondly, that's the first thing. Secondly, CD and AB are also supposed to be orthogonal. That's the second condition. And the third condition is that BD and AC are also supposed to be orthogonal. That's the third condition. Now we have already proven that AD and BC are orthogonal. So we are just left to prove that these other two conditions are satisfied, and then we conclude already that D is the orthocenter of the triangle ABC. If you don't want to call it orthocenter, you can call it circumcenter. Alright, so these two lines are perpendicular or orthogonal, we have already seen the condition. The argument, that is the angle between the lines, is equal to plus or minus pi ln 2. Okay, so we need to look for ZCD over ZAB, which is ZD minus ZC over ZB minus ZA. If you simplify, our ZD is x plus y plus z, minus ZC, which is z, we just get y plus x. Do the same thing in the denominator. Our ZB is y and our ZA is x. If you multiply by the conjugate of the denominator, you're going to learn in this case, and from there we can remember our justifications. The complex number y plus z and y bar times y bar minus z bar was purely imaginary, so these complex numbers are actually interchangeable, so we can replace x with z, and we still have that this complex number is purely imaginary, and purely imaginary means you can be written in that form. So it therefore means that all of this recurs. It therefore means that this is also purely imaginary, because the denominator is purely real, multiplying the complex number and its conjugate is purely real, numerator is imaginary, purely imaginary. So when we do the ratio, we get a purely imaginary complex number. Therefore the argument is plus or minus pi ln 2, because you're doing the argument of a purely imaginary complex number. Now BD and AC are supposed to be orthogonal, same condition. We do the affix, we do the difference, and then we also multiply and we give our recourse, and then we see that this complex number is also purely imaginary. So we can conclude that the arguments, that's the angle between AD and BC, CD and AB, and BD and AC, are all plus or minus 90. Alright, so from there the point D is the orthocenter of the triangle ABC, and we have proven. Alright, the part 2 of this question says, suppose that A and B have affixes t plus ia and t plus ib, where A and B are real numbers with t different from 0 and b. Let A prime be the image of A after a rotation through pi ln 2 about the origin O. Let B prime be the image of B after the rotation through negative pi ln 2 about the origin O. Question 1. Determine in terms of t, A and B, the affixes of A prime and B prime. Alright, so we just need to recall our definition of the rotation. If you have a rotation centered or center omega, then you want to take a point z to z prime with the angle of rotation alpha, then this equation is always true. So let us begin first. The rotation r1, okay, let's just say, okay, the rotation r1 takes the point A to the point A prime. It therefore means that the difference between the affixes of the image and the center is equal to e to the power the angle of rotation pi ln 2 times the difference between the affixes of the point and the center. The center is the origin, so the affix is 0. So it therefore means from there that our ZA prime will be e to the I pi on 2 is I times our ZA is t plus ia, then minus z0, which is 0. So from there, if we multiply, we are going to get that the affix of the image of A, which is ZA prime, is negative A plus it. Now we do the same thing for B. B now we call the rotation r2 that takes the point B to the point B prime. It therefore means that the difference between the affixes of the affix of the image and the center is e to the negative I pi ln 2, because our angle of rotation is negative pi ln 2, times the difference between the affix of the point and the center. The center is the origin, so the affix is 0. So from there we can multiply and we get our ZB prime to be B minus IT. Okay, now the next question is saying that we should show that the median from the point O of the triangle OAB is the height from O of the triangle OA prime B prime. So I tried my best to visualize what is happening, and I still came up with an arbitrary triangle for you to see. Alright, so let's just consider, okay, this is our origin, right? And then this is A, and then this is B. So this is the original triangle OAB. Now this is the triangle OA prime B prime, because A prime B prime are still on the same plane. because the points A and B were transformed to A prime B prime. So what they're asking us to show is that the median from the point O of the triangle OAB, meaning the median from O of the triangle OAB, the median is simply beginning from O and it is cutting the side AB into two equal parts at 90 degrees. They're trying to ask us to show that the median from that point O of the triangle OAB is the height from the very O of the triangle OA prime B prime. So you clearly see that this figure clearly explains what is happening. So you see that this is the height of the triangle OA prime B prime, and then the same O. In fact, let's just indicate that, okay, let omega be the median of the segment AB. All right, and we know that since it is the median, it means it cuts it into two equal parts and it cuts it at 90 degrees. And it being the height of the triangle OA prime B prime, it means that it also cuts the base of that triangle at 90 degrees and it also cuts it at 2 points. So all we need to show is that the vector or the line O omega is actually perpendicular to the base of the triangle OA prime B prime. If we are able to show this, then we have proven what is required for us to prove. I'm going to explain again. We have to show that the median from the point O of the triangle OAB is the height from the very point O, but now of the triangle OA prime B prime. So if we let these points here, that is, let the midpoint of the segment AB be the point omega. So you clearly see that this height, okay, is the same as the median. All right, and the median is cutting the segment AB into two equal parts and it is meeting it at 90 degrees. It therefore means that it is also going to meet the base of the triangle OA prime B prime at 90 degrees too. So if we are able to show that the line O omega is perpendicular to the line A prime B prime, then we have proven the required results. So let us start by finding the affix of omega. So since omega is the midpoint of the segment AB, then the affix is simply summing the affixes of A and B and dividing by 2. But the affix of A was T plus AI and that of B was T plus IB. So from there we sum and we divide by 2 and we factorize, we bring the imaginary part and the real parts together, and we get that the affix of omega is T plus I into A plus B divided by 2. Okay, now from there, now we have to show that actually happens. Okay, so we now need to remember that we are showing that two lines are still perpendicular, so we need to just look for the affix of the ratio between the lines, and then we take the argument. It should give us plus or minus 90. Then we conclude. So Z O omega over Z A prime B prime is Z omega minus Z O divided by ZB prime minus ZA prime. But we should recall that our ZA prime was gotten as negative A plus IT, and our ZB prime was gotten as B minus IT. It therefore means that our Z omega, which is already gotten here, our ZO is 0, so we just have Z omega in the numerator. We now subtract the affixes of A prime and B prime and we replace it in the denominator. So if we do a good subtraction, we are going to get this. Now it means that this affix is equal to all of this. Now if you multiply, that is after rationalizing the denominator, if you multiply carefully, so this is for you to do, I could not include everything in the video. So if you multiply carefully, you're going to get I divided by 2, because this factor in the denominator will cancel off with in fact this factor in the denominator is going to appear in the numerator and it's going to cancel off, and you're going to get an I divided by 2 as your response. So it therefore means that the argument of this is simply the angle between the line O omega and A prime B prime, which is the argument of I on 2, and the argument of I on 2 is simply pi on 2. So we can conclude that the line O omega is perpendicular to the line A prime B prime, and we have proven the required results. Alright, this is the last part of the video, problem part B. It was allocated for 5 points. Alright, the question reads, Q is a point inside ABC. The lines QA, QB, and QC meet the sides BC, AC, and AB at A prime, B prime, and C prime respectively. Suppose S is equal to QA on QA prime plus QB on QB prime plus QC on QC prime. What is the locus of the barycenters of the points AA and BB when A and B have the same sign? What is the locus of the barycenters of the 3 points when their coefficients are strictly positive? Question 3. We suppose that the point Q is a barycenter of the weighted points AA, BB, and CC. Question A. Show that QA over QA prime is equal to B plus C on A. Show that S is equal to B on A plus A on B plus C on A plus A on C plus B on C plus C on B. Hence, determine the minimum value of S. They have given us a hint. Determine for x greater than 0 the minimum value of x plus 1 on x. Precise for this minimum value of S the nature of triangle ABC. Okay, so I am going to do the first question and you are going to do the second question. So I'm going to briefly explain how you get the barycenter of 2 points, and then I'm going to just tell you what the barycenter of 3 points is, and you try by yourself. Okay, so this topic is a very important topic in the concours and in the French syllabus as well. It's a topic that the English subsystem is not familiar with, so you guys preparing for the concours just meet the topic maybe during classes or whatsoever, so the topic is always tend to be a little bit complicated, but nevertheless you have to try your best to understand the topic because it is very straightforward, very straight to the point. It just needs you to bring out your reasoning skill. Alright, so Q is a point inside ABC, and then you have these 3 lines meets those 3 these 3 lines meet those 3 segments at these 3 points. We suppose S to be this. First question, what is the locus of the barycenters of the points A, B, B when A and B have the same sign? So let us let the barycenter of these points to be G. Okay, now the first thing you have to note is that barycenter of points is just the center of gravity of those points. Okay, and we did center of gravity in pure maths with mechanics, so it is not strange. It's just that here we are going to be using vectors and we are going to be defining what the barycenter of a system of points is actually all about. So whenever they give you a point like this, A, small a, this capital A here is a point and this small a is called the mass or the coefficient. So this in fact this point here is called a ponderable point or a weighted point. Same thing for B. So for the barycenter of a system to exist, the sum of the coefficients of the various points must not be equal to 0, so it must be different from 0. Then we see that the barycenter of the system exists. So in this case, since they are asking us to look for the locus of the barycenter, it means that it already exists. Okay, so we can let G be the barycenter of these points. Now how is it represented? It means that G is the barycenter. Here's a representation, barycenter of these points. Now if G is actually the barycenter of these points, then it satisfies the relation the coefficient times GA for A plus the coefficient of B times GB equal to the 0 vector. So from here we can do a little bit of vector reduction. That is, we identify that the vector GB can be written as GA plus AB. Sorry, here it's supposed to be AB. So GB is the same as GA plus AB. Alright, so from there now we can split the B inside and we get AGA plus BGA plus BAB. Now we can factorize A plus B. We can factorize GA from these two terms, and we get A plus B times GA then plus B times AB is equal to the 0 vector. We can cross multiply. In fact, we can send BA to BAB to the right hand side. It becomes negative, and then we also identify that the vector GA is negative of the vector AG. We can now divide both sides by those two negative signs, and then we divide all through by A plus B, and then we get that AG is B divided by A plus B times AB. Alright, now from there we clearly see that if we set our alpha to be the constant B divided by A plus B, then we have that our AG is equal to alpha times A plus B. Now look at these two, they are vectors, and if a vector is a scalar multiple of the other, then the two vectors are called parallel vectors. And when the vectors are parallel vectors, it therefore means that in fact they can be expressed in this form. One can be expressed as a scalar multiple of the other. And if vectors are parallel, it therefore means that they are in the same direction. In fact, we are trying to say that the points A, G, and B are all on the same line. Alright. Okay. Now we have to construct this Barycenter. So first, if the since the set, in fact, this explanation is just for the fact that the two have the same sign. Okay, if A and B are both greater than 0, it therefore means that our A plus B will also be greater than 0. So the ratio of B over A plus B, which is alpha, will be in turn greater than 0. What if both of them are less than 0? If A and B are less than 0, it therefore means A plus B will also be less than 0. But now our alpha will still be greater than 0, because we'll be taking B, which is less than 0, divided by A plus B, which is less than 0. We are going to have negative over negative to give us positive. So when they have the same sign, we have that our alpha is positive. Now, when alpha is positive, how then do we locate this Barycenter? Like, where is this Barycenter going to be? In which position is it going to be? So we have seen that if A and B are both positive, it therefore means our B is less than A plus B, right? Because B is normally less than a number plus it when that number is positive. So if we divide both sides by A plus B, which is positive, the inequality sign remains unchanged. So we have that our alpha will be less than 1, because our alpha is B divided by A plus B. So from there, alpha, what is first of all alpha? Now if we have this relationship, right, it means alpha is simply AG divided by AB. So if we take modulus on both sides, we have that the modulus of alpha is still alpha is the modulus of A, the magnitude of AG over the magnitude of AB. But the magnitude of AG is simply the distance from A to G, and the magnitude of AB is the distance from A to B, and it is alpha and it is less than 1. So if the distance from A to G and the distance from A to B is less than 1, it therefore means that G must be between A and B. Okay, in fact, from this relationship, we have already seen that the two lines are parallel, they are in the same direction. But our problem now is to actually get where the point G is actually located. So if we want to construct, if I pick a point A here and then I pick a point B there, I link the line AB, this is my direction vector. Now since you have seen that AG divided by AB is less than 1, it therefore means that the point G will be closer to the point A. Okay, so the point G will be around here, so that the distance from A to G is, because if AG over AB is less than 1, it means that AG is less than AB. All right, so it therefore means that our constant is positive. It therefore means that our G will be closer to A, because if you see the distance from A to G is less than the distance from G to B. So it therefore means that in fact the 3 points are outlined and G is in this position. So the locus of the Barycenter of this system of these points when A and B have the same sign is simply a point G, which is in between. In fact, it is between the line segment A and B, closer to B than to A. So that is it. So like I said, the next question is talking about Barycenter of 3 points, and it's going to give you a plane. Okay, it's going to give you a plane, a point that is contained in the plane, because the 3 points are not going to be aligned. So try to do it and construct it. Comment section, I'm waiting. Okay, question 3, we suppose that the point Q is a barycenter of the weighted points A, B, B, and C. Now we have to show that QA on QA prime is equal to B plus C divided by A. Alright, so there are some basic recalls that we first of all have to do. First, we have been told that Q is a barycenter of these 3 points. Okay, so that means that this happens. That's the definition of the barycenter. It means that A times GA plus B times GB plus C times GC is equal to 0. Now that happening, we can now write, because remember that we have in a proof QA prime, and we're told that the line QA actually cuts the segment BC at a point A prime, right? It therefore means that I need to introduce an A prime because it is there, my final proof. So I'm going to write GC as GA prime plus A prime C. This is vectors. Now I'm also going to write it's like I repeated the equation. So let us write GB in the same way. So we are going to write GB as GA prime plus A prime B. Now we distribute the B and the C, and then we bring like terms together. So we distribute the B, we distribute the C, and then we add up together. We bring like terms together. So GA prime is going to be common and is going to be factored. It's going to be factored from B and C. So you have B plus C, and then you'll be left with B A prime B plus C A prime C. But now we're being told that the point A prime is actually on the segment BC, where the line QA, in fact, the line QA meets the segment BC at the point A prime. It means that A prime is inside that line. Alright, if we try to construct, we have just done it before. If you have B here, we have C there, then that is the vector BC. Now A prime is anywhere inside. Okay, it therefore means that we can clearly say that A prime is a barycenter of the points B and the point C. In the first question, we proved that if G prime, in fact, we proved that G is a barycenter of 2 points when A and B have the same sign, and we saw that N is inside, in fact, is between the line capital A and capital B. So here A prime is between that line. It therefore means that we can say A prime is a barycenter of those 2 points. Okay, so A prime being a barycenter of these 2 points, what does it mean? It means that we take the coefficient B times A prime B plus C times A prime C equal to 0. Now we clearly see that this component in our expression, in our equation here, is actually what we have here, so we can equate it to 0. So from there, we are just going to have these 2 things added up equal to 0. Then from there, we can send GA to the right hand side, and then from there, we know we take modulus on both sides. Okay, this was supposed to be Q. Okay, you're supposed to be Q, not G. Anyways, I believe you're getting the point. It's supposed to be Q, not G. Alright, so you have AGA to be equal to, if we take modulus on both sides, the modulus of the vector will just give you GA prime into B plus A. It therefore means that our GA will be equal to B plus C divided by A times GA prime, meaning that GA over GA prime will be B plus C divided by A. Alright, so let us now see a different approach in getting it. Alright, so there I was actually using the proving itself, but here we are going to use some properties of barycenters. In fact, associativity of barycenters. That's basically what we are going to use here, and that was what I was, that's the concept I was actually proving in the previous slide, the concept of associativity of barycenters. Okay, so let us see how we can do this. Now we have that QA meets BC at A prime. It therefore means that the ponderable point associated to A prime will be A prime comma B plus C. So since A prime is on the line BC, it therefore means that the coefficient of A prime will be the sum of the coefficients of the B and C. Okay. Alright, so now since Q is the barycenter of these three, it therefore means this B, B, and CC will just be replaced by A prime, B plus C. So Q will be the barycenter of AA, A prime, B plus C. And with that said, it means that A Q A plus B plus C Q A prime will give you 0. So we can send B plus C times Q A prime to the right hand side, and then we divide all through by A, and then we take the modulus on both sides. The modulus on the left hand side we now divide by this. Modulus of this gives you Q A, the distance from Q to A. Modulus of this gives you Q A prime equal to B plus C divided by A, and the proof comes out. So this is another way of proving it. Okay, now question B is saying that we should show that S is equal to this sum. Okay, so firstly we have clearly seen our S is Q A on Q A prime plus Q B on Q B prime plus Q C on Q C prime. We have already seen that Q A on Q B on Q A prime is B plus C on A, which is the same as B on A plus C on A. So let us verify the rest, and then we add all of them together. Okay, so we also know that QB meets AC at B prime. So the ponderable point that is associated to B prime will be simply B prime and then A plus C, because QB meets AC. So we need to add the coefficients of A and C, and we associate it with the point B prime, since B prime is a barycenter of A and C, since it is actually inside A and C. Okay, so from there it therefore means that our Q will be the barycenter of the system AA, and then B prime we are going to replace it with, in the place of B and in the place of A and C. Here was supposed to be in the place of A and C. We are going to replace it with in the place of A and C, we replace it with B prime A plus C, and then we are going to be left with our capital B, small b. So that is why we have that small b times Q capital B, then plus A plus C times Q capital B prime is equal to 0. So with that said, we can do the same thing we did here, and then we take the modulus on both sides, and then we obtain that QB on QB prime is A plus C divided by B. And then finally the same thing, since QC is going to meet AB, here it's supposed to be AB not BC, so QC will meet AB at a point C prime. It means that here we just replace C prime, okay, and here is going to be A plus B. Alright, and then now the remaining point is going to be the point C. So it therefore means this is what we have: C QC plus the A plus B QC prime is equal to 0. We do the same thing we have done, and then we simplify, and then we get what we have. Now what is S? Our S is simply summing those respective distances, 1 plus 2 plus 3, which will give you our 1 is B plus C on A, our 2 is A plus B on A plus C on B, and our 3 is A plus B on the C. So from there we can clearly simplify, and then we have B on A plus C on A on B plus C on B, A on C plus B on C, and then we try to group the A's and the B's together, and we arrive at the proof. Finally, we are asked to determine the minimum value of S for, and they are giving us a hint. Determine for x greater than 0 the minimal value of x plus 1 on x. Precise this minimal value of S, the nature of the triangle ABC. Alright, so let us use a hint that has been given to us. Alright, so we are going to study the function, we are going to study the variations, and we draw the variation table of the function g, which is x plus 1 on x, on the interval x greater than 0, meaning from 0 to plus infinity. So our g of x is equal to x plus 1 on x. It therefore means our g prime will give you 1 minus 1 on x squared. If we simplify, we get x squared minus 1 all divided by x squared. At the turning point, we know g prime is equal to 0. So g prime equal to 0 means that the numerator has to be 0 because our denominator cannot be 0. And the numerator being 0 means x is negative 1 and x is 1. But since our x is greater than 0, in this case, it means our x is equal to 1 only. Now, what about the variation table? So our variation table, first we indicate the domain of definition from 0 to plus infinity. So we have 0 plus infinity. Now, if you look for the limit at 0, we are going to get 0 plus 1 on 0 from above. We give you plus infinity. It means 0 is a vertical asymptote. Now, from there, we also need to indicate in between the domain the x coordinate of the intercepts as well as the x coordinate of the turning points. But x cannot be 0, okay? So, but if can g of x be 0? No, it's impossible. Since x is positive and 1 over x will also be positive, you cannot add two positive numbers and we get 0. It means that g of x can never be 0, and also x cannot be 0. So we are just going to impute the x coordinate of the turning point, which is 1. Now we need to actually determine from the variation table if this turning point is a minimum turning point or a maximum turning point. Then from there we deduce the minimum value of that function. Then we use it to determine the minimum value of s. Alright, so the sign of g will be needed and the shape of g will be needed. But to do this, we first of all need to study the monotony of the function g, where we have g prime of x greater than 0 if and only if x squared minus 1 over x squared is greater than 0. Since the denominator is already positive and you need to divide two things and the result has to be positive, then this is possible if the numerator is positive, since the denominator is positive. If you solve this inequality, you're going to have x less than negative 1 union x greater than 1. But x less than negative 1 will be removed because our domain is a positive interval, so x greater than 1 will be accepted. Alright, so it means the function is g prime is greater than 0 when x is always greater than 1. Now g prime is less than 0 if and only if the g prime is actually less than 0. Now we want to divide two things and the result has to be negative. Now both numerator and denominator are supposed to have different signs. We already know the sign of the denominator x squared is positive. So for this to happen, the numerator has to be negative. And if you solve this inequality, you're going to get x between negative 1 and 1. But the negative interval will be removed. So we can begin it from 0 because that is where our values of x begin. So g prime is negative when x is between 0 and 1. So we come back and fill our variation table. Between 0 and 1, our sign of g prime is negative. And between 1 and infinity, meaning greater than 1, the sign of g prime is positive. Now from there, we clearly indicate the limits at the bounds, okay? So the limit at 0 from above, as you saw, is plus infinity. And g prime being negative means that the function is decreasing. It decreases to g of 1, which is clearly seen as now the minimum turning point. And then it now increases from there to the limit at plus infinity, which is plus infinity. So in conclusion, the minimum value of x plus 1 on x is g of 1. And what is g of 1? 1 plus 1 over 1, and 1 plus 1 over 1 is 2. So it means that the minimum value of our function is 2. Now let us see how we can use that minimum value to determine the minimal value of s. Alright, so how then do we determine the minimum value of s? We have seen that s is equal to b on a plus a on b plus c on a plus a on c plus b on c plus c on b. So we can clearly write it as b on a plus 1 over b on a, because a on b is 1 on b on a. We do the same thing for the rest of the fractions, and then we clearly see that this b on a is here. We can call it x plus 1 on x, plus we call this one y plus 1 on y, then we call this one z plus 1 on z. We clearly see that those are similar functions and will have exactly the same minimum value of 2. So it means that the minimum value of s is the minimum value of this plus the minimum value of this plus the minimum value of this. But since the minimum value of x plus 1 on x is always 2, it therefore means that the minimum value of x will be 2 plus 2 plus 2, because we have identified that b on a plus a on b can be written as b on a plus 1 on b on a, which resembles x plus 1 on x. So the minimum value will be 2. Same thing applies for the other two, and at the end of the day we get that the minimum value of s is equal to 6. Finally, we have to deduce the exact nature of the triangle ABC with this minimum value of s. Alright, so let's just draw any triangle. Okay, so let's say A, B, and C. Now cure is any point inside, and then we have that cure A meets C, B, C at A prime. We have that cure B or B cure meets this other man at B prime, and then we have that C cure or cure C meets AB at C prime. Now we have also had that in fact we have seen that the minimum value of this of B on A plus 1 on B on A is actually equal to 2. Alright, it means that cure A is 2 times cure A prime. Same thing, cure B will be 2 times cure B prime, and cure C will be 2 times cure C prime, because cure A on cure A prime will be 2. Cure B on cure B prime will be 2, and cure C on cure C prime will also be 2. Let's see if that is possible. Let us see something. Okay, the minimum value of this function, we have seen it is 6. So we have to precise for this minimal value the exact nature of the triangle S. Alright, now we see that for, in fact, B on A must be equal to 1. That's what we are trying to say. So B on A must be 1. Okay. C on A must be 1. In fact, this sum here must be equal to 1. This sum here must be equal to 1. And this sum here must be equal to 1. So B on A must be 1 and A on B must be 1. That's it. So if we try to rearrange back to have cure A on cure A prime, we are still going to have cure A on cure A prime to be, since we previously proved that our cure A on cure A prime was B plus C on A. So if we still rearrange to come back to this specific, we are still going to see that cure A on cure A prime will be 2. Cure B on cure B prime will be 2, and cure C on cure C prime will be 2. So it therefore means that these relationships hold. And when these relationships hold, clearly this triangle is an equilateral triangle, since the distance from A to cure is, in fact, the distance from A to cure is 2 times the distance from cure to A prime. If you look at this very well, the same thing goes for the rest. Okay, so since you are deducing, precising the exact nature of the triangle, then cure is said to be the how do they call it, the isobarycenter of ABC, or the circumcenter of ABC, or the orthocenter of ABC. Okay, so with that we said that the triangle ABC is an equilateral triangle. Alright guys, thank you guys for watching the video. If you watched till the end, appreciation to you. Like the video, share the video with your friends who are preparing for the concours. Comment so that I'm going to, because I want to start preparing paper 2 already. So the comments on this video will better guide me on what you actually need. That is, if the explanations are good, just comment on the video so I should know how to prepare for paper 2. Thank you guys once more for watching, and see you in paper 2.